Hi, and welcome to another edition of Easy Theory. Today we're going to continue our theme on recursion and talk about a more applicable problem. So, Towers of Hanoi and things like that are probably not as real-world application as you might like, but the application we're going to talk about today, sorting, really is. So, what is sorting? So, the basic idea is we got a bunch of data, we want to sort it. So if I have, let's just say, a bunch of numbers like this, just as an example, we want to be able to transform this list into a list that is in some sorted order. So let's just say ascending order, but what we're going to do will generalize to any type of sort that you want, like descending or any type of sort. So the sorted order in this case is 0, 1, 2, 3, 4, 5. So the smallest element is at the very front, and the largest element is at the back. Okay, so what we want is some type of algorithm that will take any array or any list of any size with any set of elements, and as a result, produce a list that is in, let's just say, ascending order, but you can change the order if you wanted to. So that's what we're actually going to do here. So how do we actually do this? So what we can do is use recursion. So if we can divide up the list into multiple pieces, and each of those pieces is sorted by themselves, supposing, then could we merge these two smaller lists into one bigger list that is also sorted? So I like motivating this with an example. So suppose that we have the lists 0 to 4 and 1, 3, 5. And what I want to do is I want to put these two lists together into one sorted list. And I want to do that as easily and efficiently as possible. Well, what I could do is I could just put the two lists together and then call sort on that, but that's the problem we're trying to solve in the first place. We're trying to sort the list. So instead of just putting these two lists together and then just sorting them, is there a better way we can do this? So we can note here that each of these lists independently is sorted. It's just that the elements, it's not like all of these elements are always smaller than these ones. So it's like the order can go from the first list and the second and the back to the first, second, and so the list can actually be interleaved in some sense, but the lists individually are sorted. So how do we actually do this? Well, what we can do is this. So this is what we're going to call merging, which is we're going to look at the first two elements of the element in the first list, first element in the second. Well, the smallest element among all of the elements must be one of those two because both lists are sorted. So what I'm going to do is I'm going to look at just those two elements, no other ones, and I'm going to take that element, which is 0 in this case, and put it into this list that we're making down here. So I'm going to cross off this 0 because we're done with it after I put it into the list right here, which is 0. Okay? So then now, here's the crucial part. I'm not looking at this 0 anymore. I'm looking at the first, quote-unquote, first elements that I haven't picked yet in the two lists, which is this 1 right here, but this 2 also. So now I'm going to pick whichever one is the smaller. If they're the same, it doesn't actually matter which one you pick. But in this case, one of them is smaller, and I'm going to pick the one that is smaller, which is the 1 here, and insert that into my list. Now I'm going to look at the heads, so to speak, of the lists, of the things that I haven't picked yet, which is this 2 and the 3. And so the 2 is next, so then the 2 goes in. Then we look at the 3 and the 4 here because those are at the beginning of the list. And then the 3 one is smaller, obviously, so I pick 3. Then I look at these two lists, these two numbers, and the 4 is smaller, so the 4 goes in. And actually, in this case, this list is completely exhausted. So we can actually just add everything from this list straight in. We don't have to compare anything. Well, there's only one element to add, which is the 5 in this case. Okay, so this whole idea of merging is taking these two lists that are already sorted and then producing a list like this. And we can do this in the size of the two lists right here. We didn't have to go through the lists multiple times. We just had to go through both of the lists in tandem in some sense. And then we can just produce this list right here. Cool. So then how do we actually use this idea of breaking up the list into smaller pieces and then merging the pieces back together, assuming that each of the original pieces is sorted? Well, what we can do, since this method clearly works for two lists that are sorted, let's just break the original list into two pieces, and then, supposing we have solved both of those, we combine the two lists together using this merge. So that's what is usually called merge sort. You wonder how some of these names could be made. Well, it's merge sort. Cool. So let's just say we have a list right here. So again, as always, I should specify what the types are. So this thing is a list, which can have anything, can be of any size, it doesn't matter. Well, so now we got to think. Well, in every recursive problem, every single one, there is a recursive case or multiple and a base case, something to stop us from having to recurse going down to make smaller and smaller lists in this case. Well, what is the smallest case in here? Well, if I have a list of one element, just one element in the list, it's already sorted. So if the list has more than one element, I may need to do something. But if it has exactly one element, then we're done. So that's what we're going to do here. So I'm going to set n, because I'm going to be using it multiple times, to be the number of elements in that list right here. Okay. Well then, if n is equal to 1, then the list is already sorted. So the only really interesting case is when n is bigger than 1. So if n is at least 2, I'll just say it that way, then what we need to do is to recurse on both sides, because I want the first half to be sorted and the second half to be sorted so that I can merge them together. And we're assuming by recursion that each of the pieces is actually sorted. So what I'm going to do here, oops, accidentally undid there. So I'm going to just call merge sort on the first half of the list. So here I'm just going to say first half of L. There's a little bit of a technicality there, which I'll address in a second. And then B, I'm just going to call merge sort on the second half of L. I'm just going to recursively go on the first piece, assume that it's sorted, recursively go on the second half, assume that it's sorted. And you may be thinking, well, why do you use two pieces? It's because the merge procedure works with two pieces, so that makes sense. But why would we use half here? Why don't I just say like 90% and 10%? So put in the comments whether you think we really do need half and half here, or we can split it by some other metric. But it turns out half is the quote-unquote best thing to do here, but put in the comments what you actually think if we did it some other way. But if we just did this, the array doesn't change. The actual list doesn't change because none of these steps actually change the list in any way, so it doesn't actually help us until we actually do the actual merge operation, which is merge the first and second half of L. Just like how we did before, where we had the two sorted pieces and then we take the first two elements, find out which one's the smaller one, then put the new one, the smaller one into the new list, and that's what we actually return. Cool. So what was the minor technicality that I was mentioning? Is that what if n is odd? So what if n is odd? Then this first half doesn't actually make sense, because if you take an odd number divided by 2, then that doesn't actually really help us here. So what we want to do, and this is what is actually done, is if n is odd, in one of the recursive cases here, we round down, and in the other case, we round up. So what we really do here is I put a step right here, which is m is another variable, which is going to be n over 2 floor. And instead of first half here, it's going to be the first m elements of L. And here I'm just going to say, just for simplicity, the rest of L. Okay, just to keep things simple. You could make this formalized, but I want to get the whole idea across first. Okay, so this actually works because at some point we're going to recursively go down, 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 because we're dividing the list roughly in half every time. And at some point we're going to have exactly one element, but we don't do anything with one element. So whatever recursive case that went to, that's going to have a list with just one element. And in the second case, it may need to recurse again, but again, it's going to have one element. So at some point, at the very bottom of the recursion, we're going to have two lists with exactly one element in them. And then we're going to merge those two lists with one element in them. And we're going to now have a sorted list with two elements in them. And then the net recursive case up above that is going to eventually have two lists that are both sorted of size 2 each, and then we'll merge those together, and then just keep going over and over and over. So one thing you may be thinking, well, this function doesn't actually return a list at all. So like there's no return statement here. So this is actually what is called an in-place sort. And what do I mean by that? It means it doesn't actually create a new list, it just modifies the existing list in place, which is what we really want here. Because if I'm trying to create a whole bunch of new arrays, that's going to slow the algorithm down. So if I just swap elements in the existing array, that's going to actually be a lot faster. It doesn't change the asymptotic running time, what the runtime is overall, but it might make a difference in real-world practice. So that is merge sort, a recursive algorithm for sorting a list where all we have to do is just split the list into multiple pieces, assume that each of the halves, in this case, are sorted, and just combine the two sorted halves, and we know how to do that. So hopefully that was interesting. Leave a comment down below if you have any other recursive sorts that you think are interesting. As always, please like and subscribe to the channel. It really helps us out, and I'll see you next time.